So let's us come to the follow. Sorry. So let's us begin the second topic of today. That is the robust regression. And these techniques are different from what we talked about before. That was the outlier diagnostics. So the outlier diagnostic is about identifying where's the outliers in training. And we talked about three methods. That was hat matrix, residual analysis, and the Cook distances. And in fact, we now know that hat matrix is the one that used only the input features, so it can identify the outliers in the input features. That is called the high leverage. Meanwhile, for the residual analysis and Cook distance are based on the residual between the measurements versus the estimation from the linear regressions using the input features from training. And actually, as we mentioned, the Cook distance is the one where we transpose y minus x beta. Yeah. So it's like the square distance. And actually, Cook distance is the one that could calculate this residual term in a much simpler way compared to the residual analysis. And in fact, you can run the Cook distance much more efficiently compared to the residual analysis. And they actually proposed a new formulation where you can integrate the hat matrix into the Cook distance. And that's become like a new formulation, and that's going to be in your homework where you have to analyze, like the similarity or difference between the Cook distance. Yes. Yeah, it was this L2 norm of the distance. And you have to analyze difference between the Cook distance versus the hat matrix. Yeah. This is just to recap. So let's go back to what we are going to talk about now. We are going to talk about the robust regression. They are like the techniques where we suppress those outliers given that we know the locations, and or if we don't know the locations, we may run an iterative approach to find it. Or alternatively, if we don't care about where are the outliers, we may consider the following techniques where they actually only try to suppress the effect of the terms with higher residuals. That's it. Okay, so let's go over each of them, and that may help. And in fact, here I provide some notes for each of the method. Okay, for the first method, that is the weighted least square. This one is the one where first you assume you know where the data points are bad, or on the other words, maybe you've run the Cook distance or the hat matrix before. So you know which locations of the data pairs xj and yj that are having problems. And then with the information of those locations, you suppress the impact of these data points when you are trying to estimate for the model parameters beta. So that's your first technique. And in fact, the following techniques are going to be similar to the weighted least square for the fact that they actually solve for the model parameters by solving a minimization problems. For problem number one is like you are doing the argmin, So here L is the weight. So if you just write this down, like as matrix vector multiplications. In fact, where L is a matrix, you can think of L as a diagonal matrix, right? And that means that, if you put this coefficient of the diagonal matrix to have like high value, that means the location of the measurements corresponding to that will be emphasized further. And that's why if you also know which location, on this L matrix that is diagonal, that you want to suppress, let's say this location, the one after it, that you want to suppress, you can put low value on this diagonal coefficients. And this is like a technique that you will see. And the thing is, as you can see, because we somewhat predefine this L matrix, or on the other words, we assume that you know what this L should be, then the algorithm would just find or estimate the model parameters beta by solving these least square problems. Likewise, for the second technique that is called the robust regression, like they are like a loss functions. What it means is that they just replace this L2 norm with other types of norm. That is, for example, you may use, I'll use this color. You may use the L1 norm or Huber norm to estimate for beta. And the reason for that is because if you think about this least square error, the least square error or the L2 norm here will tend to emphasize when the value of the residual is large. For example, if you think about, plotting f of x where x is square function and this graph is x, you know that if x is 1, right, this is 1. But if x is 2, this is what, 4? And so on and so forth. It's like the square of that x. And the thing is, when your residual is large, it will have the large impact on your residual function or on your the loss function. And because of that, people also propose changing this square error to maybe L1 error or Huber norm error, so that when x is large or when your residual is large, it will not have such high impact. And in fact, another group of methods that is similar to this is called the M estimator. And this M estimator is based on using the mean absolute deviation. In fact, what is similar to the robust regression is that they are relying on the L1 norm. But this L1 norm is weighted by some absolute deviation. Okay, so, but at the end of the day, if you consider these three methods, they're still similar in the sense that their optimization problem will have only one optimized variable, that is beta, where you may assume to know the fixed weights just like that one, if the weight is known. But if weight is not known, then it becomes like the other two methods where you just provide the weight of the absolute deviation, or you just provide the new function that will suppress the impact of those high residual terms. Or also that high residual terms will also related to the outliers in your training. Okay, then that's it. The three methods that we will go through today. And in fact, we have another method that was the false method. And this one, the difference between the false method and the rest is the fact that, well, for this one, you will reestimate beta. Given that you update the weight, the similar weight to the technique number 1, that L weight here. But the thing is, this algorithm will iteratively estimate the weight, then use that re-estimated weight to estimate beta. Then with the new beta, that will go back to re-estimate the weight again and perform this loop of iterations until it converge. And there are actually like a conditions to check whether or not your algorithm will start to converge. Therefore, the difference between this technique number 4 versus the rest is the fact that in this case, your optimized variable will not just beta. It will be both beta and the weight. Okay, so now let's go through this method together. Okay, here again, I just want to, recapture the system of the linear regression where our input features in training is denoted by this matrix X, and the number of rows are going to be the number of training data. And N here is the dimension of your input features. Yes, and in this case, we will suppress each input training data that's aligned in the row by using this L matrix. So you can imagine that if this is our X, right? X beta, you can see that beta, in fact, doesn't really have impact on which row that we would select off, right? But of course, this selection of L will have impact on the row of X and the row of Y. Okay, let's say if we were to decompose it, then you will have L X, sorry, this is a matrix, beta, which is a vector, minus L Y. And if L is a diagonal, right, we just assume a simple case. But in this algorithm, the weighted least square, we assume that L is known. Okay, we sometimes use the word preset to refer to the fact that, it's kind of like you estimated before. Predefined. Okay, and if you think about the fact that, when you decompose L into each term, it will turn out just like that formulation above. And if L is a diagonal matrix, then that means that, this diagonal coefficient will select which row on X, or maybe it can be used to emphasize which row on X that it want to put the higher weight on, right? And that has nothing to do with the vector beta. And if you think about, again, if you have the same L and you multiply that to the training measurements, then again, that coefficient will select, or maybe it could emphasize which one, it could emphasize which row on X and Y that's going to be, of high value or low value. And therefore, you can use this matrix L to suppress the error, or maybe to suppress the effect of the outliers if that row is outliers. And the question is, how could you construct L? In fact, you can, come up with a random guess of the value of L. But I think the easiest, I shouldn't say that you come up with a random guess, because you cannot really guess where the outliers are going to be. But let's put this way. We can define the location that we want to suppress. Maybe the outliers locations, just put that way. The locations of outliers using the hat matrix. Or Cook distance. Right. After you define the location, then with this location you can put like a weight like 0, 0, 0, 1, and for the rest of that it will be 1 on the diagonal line. Then yeah, it will work. It could provide you like a rough way to suppress the outliers in your system. And still with this weight L, the bill here is like L transpose L. Therefore, you can estimate for beta from this least square optimization. And of course, if you ask, okay, if you have this L, right, it suppress the coefficients, it suppress the data pair xj pair that you don't want. And with that, it will also automatically reduce the impact of the residual from these outliers. And as a result, your estimation for beta wouldn't be dragged down, or maybe it wouldn't be dragged by the impact of this outlier as much compared to the original linear regression. So that's the key idea of this algorithm. Right, the next algorithm will be, in fact, this is like an example. Okay, so let's say if we know that this point, are identified as outliers by maybe hat matrix or maybe Cook distance. Let's say if we choose to keep this outlier, right, and perform the normal linear regression using just the normal least square optimization, you will get the line such as the red line here. Okay, this from the least square estimation in linear regression. Or on the other words, they actually referring to the optimization problem that is argmin beta x beta minus y. Yep, right. But if you could use the weighted least square, and at least roughly where those outliers are going to be, and you kind of put a very low weight to these points, then you can get the dashed line below here. Yeah. And therefore you can see that the difference between weighted least square versus the generic least square, as you can see, because you weighted those data pair that you don't want by the L matrix down, it doesn't have such impact on your estimated beta, and therefore the mapping will go with the majority of those measurement points. Okay, that's it for this method. This is just an example of what it could look like. Yes, and here, as you can notice, they actually use the diagonal matrix, as I mentioned before. Yep, and don't forget that, if L is the diagonal matrix, the square of it is just, you could just calculate it by doing the square of the coefficients on the diagonal line. Yep, just don't forget that one. Right, and next technique, as I mentioned before, these techniques are the one where you intentionally, like, you don't want to care where are going to be the outliers, but you know that there may be outliers in this data samples, and therefore you go with the conservative choice of the norms used in the cost function. And if you recall the fact that, okay, when we estimate for beta, we usually use the argument, right? We minimize the error, the residual between y minus x beta. And we know that, if we use L2 norm, very likely the term that caused this high residual will be the one that dominates your decision for beta, right? But if you change from the L2 norm to other norm like L1 norm, or maybe Huber norm, things will be better, because this term will not give high weight on those high residual points. And you can see the difference of this function as follow. Let's say if R here denote the difference between your measurements and your estimated measurements, your prediction. If dual residual remain 1, right, then what happened is that your Huber function, just like your L2 norm function, they actually could well suppress your residual, right? But the L1 norm will be the one, that don't suppress it that much. Anyway, when your residual go beyond, like from 1 up to 2, and maybe 3, 4, and so on, you can see that L1 norm is the one that give the lowest weight towards this high residual. And if you compare between Huber and L2 norm, you can see that Huber will actually progress much slower. And in fact, Huber and L1 norm could be very similar if you give it the same slope. And that means it depends on how you set up your slope parameters. In this case, for example, people normally set it up to be m, where m is like your magnitude for the residual term. Like this one, if it's 1, right? So your residual will be, your loss function when r is larger than m, where m is 1, will be function like this, right? So you can see it's like this slope here and this one here could be the same. It could be adjusted to the same if you just change the value of m, right? Yeah. So that was it. In fact, just that. And I mean, in this picture, you may not see the difference as much, because this is 2, it's mapped to 3, okay? But if this is 3, then this become what, 9? And this become what? Maybe 3 minus 1 over 2, which is much lower. 3 minus 1 over 2 is 5 over 2, right? Meanwhile, this one is just 3. This one, in fact, it should be lower than that. Maybe there's some errors when I plot this function, because I might forget the scaling. Maybe there's some scaling up here, that's why. Anyway, just letting you know that, in fact, because of the square here is actually put high emphasis. It's actually like put the high emphasis, or it's highly emphasized the high residual term. That's it. And yeah, these techniques are actually telling you that you could go by without caring. You could win by without caring where are those outliers. You could just, do the conservative decision by using maybe L1 norm or the Huber norm. That's it. Okay, maybe in fact I should use Huber function. Yeah, that's better. Okay, and the next technique, which is similar to this technique where instead of knowing where those residual, they actually consider changing the function. And this case, it's called the row function, where this row function, if it's just a square function, f of r square, then it becomes the normal generic least square. But if this function is L1 norm, then it could, if it's just L1 norm without anything else, without this one, it become like an L1 minimization. If there's no such term, it become L1 minimization. But in this case, we also consider another alternative where the row function is L1, but also it has this standard deviation normalization. And in this number 6 here, the standard deviation is signifying that they could be the same for any residual. But the thing is, even if it's the same, but anyway, because when we want to minimize this such residual that is Rj, and I'll just provide that Rj beta will be equal to Yj minus X transpose beta. In fact, it should be Xj, right? Should be that one. Okay. Thing is, this sigma is signifying the standard deviation. Not standard deviation, sorry. If Rj is the L2 norm, okay, or maybe if this row function will return this Rj residual into maybe L2. If it's like this, then this sigma will be standard deviation. But in our case, since we want to consider the row function to be L1, then this becomes the absolute deviation. Or AD. And in fact, for the whole entire residual, you should get the same absolute deviation, right? But the thing is, in order to make sure that you will be normalized in the same manner, it just turned out that this absolute deviation sort of could be, I'll put this way, it could be adjusted to provide the same normalization, but in our case, this deviation could be different. That is, if you think about the fact that, okay, I'll put it this way. For this algorithm, one way that you can normalize it is to calculate the absolute deviation for all j terms, and that could work. But the thing is, in this formulation that we are focusing on, in fact, because the deviation that we provide here are the deviation corresponding to the term up top here, and we want to make sure that this term is normalized, and because of that, at the end of the day, you may get different sigma j instead of the same sigma j. And that is because we are defining our sigma j to be k times the maximum absolute deviation. Yep. Sorry, the median absolute deviation. And that's why, this term could be depending on the yj that you get, y hat j. And I think the key of this algorithm is, well, we have to scale it with some k factor. And for that, this k factor is defined to be 1.04826. And in fact, we have provide you the derivation of how this number came from. But in short, I'll just say it. This number came from the fact that if you want to normalize this residual to be like a residual of 1, then that sigma should be equal to 1 absolute deviation. And to cover 1 absolute deviation, you have to find what is going to be the range for your residual. Okay, I'll put this at residual. You have to find, here r equal to 0, but this is r equal to something, and this is r equal to something. It's like you have to find the upper bound and the lower bound for your r, such that this sigma here will cover 50%. And here, because its absolute deviation is, by definition, is only 50%. So in that case, because we also assume that the distribution of this residual will be like normal standard deviation, the normal distribution. Therefore, we can go through some process of finding it. And here are just the procedure of how you would find that scaling factor for k. And yes, I have already provided you the derivation. And yes, when we try to find k, we kind of consider the median absolute deviation for all j. So, yep, that is something for you. You can go back to, recap, like what are these. And I don't want to go through this again because, in fact, I believe that with your basic, you may be able to know exactly what it is. And it's not our main point. Anyway, just know that the regression for M estimator is optimized. The beta that obtained from the M estimator is obtained by the following equation. But it can have some alternatives, like maybe your sigma j here could be adjust per cases by using deviation per samples. Okay, that could be an alternative case. That's it. That's all. And yes, your k is 1.4826, or actually came from a derivation of the fact that you want this standard deviation to cover only 1 absolute deviation, which is about 50% of this normal distribution. That's the main point of this algorithm, right? So let's go through the one that is more important, and I will put it this way. In fact, to me, this algorithm kind of put things together, and there are many components that we've learned today. So for example, we learned about, that we can solve for beta using some least square, but the thing is we can also put on some weights so that we can emphasize whether or not this data sample J pair, the J pair here, are actually to be removed or to be kept, right? Or maybe you could weight it with high impact or low impact. And for this algorithm, it will be the one that, it will not only optimize for beta, but also for the weight. So, okay, this line are more like the update formulation for beta, but I'll put it this way. Formally, if you were to write an optimization problem for this algorithm, will be it should be in this formulation, more than that one. This one is like the update. Okay, I'll put it this way. This problem formulation. Formulate. Okay, I'll just put as problem form. Okay, yeah, but this is more like the update statement. That is, suppose that you got what is the WJ is, then you can use that WJ or that was estimated by the previous iteration to update for the new beta. And once you have new beta, you can use that beta to update for your new WJ. So actually this algorithm will combine everything that you've learned from today. And in fact, you will see that they actually use the hat matrix to help you calculate the update statement for the weight W. Okay, so let's begin. Okay, so generally the iteratively reweighted least square is like the iterative process that consists of the following process. So first, they will estimate for beta. That came from, maybe the linear regression and compute the residual. So you first estimate beta with linear regression where, in fact, there are outliers. Where there are outliers. Still exist. And compute residual, in which if this happen, that means that the residual that you computed from this step will be the one that have high residual, right? Because residual, because they are outlier, right? It has high residual because of outliers. After that, you will find which points then are having, which points in your training data that have high leverage, and then estimate the standard deviation of those residual. Okay. After that, you will start to compute the weight to suppress the effect of those coefficients. That was the high leverage coefficients. And yes, this standard deviation will be something that will scale. I cannot remember what was the scaling was for, but it's like part of the process to make sure that your weight will be consistently updated. So after you compute the weight, you then use the new weight to update your beta. And once you have your new beta, this beta will be something that, will go back to re-estimation. Sorry, now you have new beta, you don't need to re-estimate again, but you can now go to compute the residual. If the residual is still high, that residual will indicate that you still have to go through the process of finding the new leverage and the new high leverage. Then with that new high leverage, you will then find a way to suppress it with weights. And once you have the new weights, then you update for beta. Okay, so when you recompute beta, you will use this formulation. This is actually in your step 4. Okay, and when I was in the class, I didn't really emphasize on this because I was thinking that maybe I didn't give you the homework, but what I forgot is the fact that it's actually combined a lot of things that you've learned today. Okay, anyway, I'll just remove it for now, but you will see the procedure in the next slide. Okay, so here's the procedure. First, you calculate beta. Don't forget that you calculate beta simply by doing the pseudo inverse of x. Right? If I remember correctly, the formula is something like this. After that, you have beta, then you use that beta to find your residual for each term. And please don't worry, if it's like for per term like this, you can actually do it you can vectorize it and do it all at once for all J in training samples. Then, in the second step, you will then start to find then which J that are having problems. So, yeah, you have X here, you can compute the hat matrix, right? After you compute the hat matrix, or maybe you can use X multiply with beta T, because this beta T came from this X transpose X inverse. So, that hat matrix is simply, sorry, that should be Y, not beta. That's simply X transpose X inverse X, right? Yeah. After that, after you have your hat matrix ready, then you start to find, you then start to find the normalized residual. So you go back to that residual that you computed before, you then normalize it with 1 minus the diagonal coefficient of the hat matrix. Or you could use this formulation, like you can use either the formulation on the top, A or B, where your second formulation will also encode the deviation of your absolute deviation of the residual. So it's like the first one you didn't scale it with the absolute deviation, but the second one you did. Okay. And yes, notice that your K will still be the same, but this big K could be something else that you find suitable. I cannot remember what K that I put when I implement this algorithm, but I've done it before. If I remember correctly, it's like just value 1. Yeah, something like that. Okay, after that, after you have your residual, normalized residual, then we'll then use that normalized residual to find a new weight. And how is that related to your weight? You just look at the fact that once you normalize it, the value of your normalized residual shouldn't exceed 1, right? And if that residual is high, then that means your weight will be low because you negate it by 1 minus, right? And if the residual is just higher than 1, like exceedingly high, then you just put it as 0, because it's kind of suggesting that data point at the J training sample point shouldn't be included into your estimation for the linear regression, right? So after you have the matrix debut, after you have this debut for each J, you put it back into the diagonal matrix. And after that, you solve it with the weighted least square problem. You solve for beta with the weighted least square problem. And once you have your new beta, I'll put this way. Once you have your new beta, you can, it's like you can update it with some optimization problem, or you can choose to update it with this pseudo inverse, right? After you have your new beta, then you start to use that new beta to recompute your error or maybe your residual again. And this procedure should stop once it converges to maximum number, or if your residual goes close to 0, or maybe if you could set up a threshold to say when to stop. Updating. And as you can see, E here is a residual for each term, m terms, right? And you can see that that's actually nearly identical with this one formulation, RJ. So you can use E to replace RJ and then recompute it again. Okay, right, so that's the procedure of iterative reweighted least square. And here's some example of the result. Like if you apply, each algorithm, you use least square, the generic least square, and with the data samples that have outliers that we've seen before, these points are outliers. You can see the least square will probably be the only one that get dragged up because of the fact that the least square will somewhat put high emphasis on the point with high residual. Meanwhile, the rest of the algorithm, like the Huber laws, L1, iterated weighted least square, or maybe LTS, which is like a new algorithm that I haven't mentioned. It's the least trimmed square estimators. They are another robust algorithm. And you can see that all these methods could remove the impact of those outliers. Meanwhile, this one is slightly different. You can see that, because the data is much more challenging. It's like previously we said that maybe these points are the outliers, but you can see that there are many points that could be outliers. And also, if you look at the least square, right? This is the case where your least square, Huber laws, and maybe iterated weighted least square are not that different from one another. Like they could still be dragged up and dragged down. But anyway, the method that outstandingly give you different results is like the LTS and the L1. So, but I think L1 is not working properly here because, this point, is outlier and it's kind of dragged up. So, yeah, maybe what you should take from this slide is the fact that, one thing that you could do is that you run the generate least square for the linear regression and see if you get different result, and to see whether or not there are some divergence, such as like this case. If it's not, maybe you have to try other algorithm. But I think what you should do before trying so many algorithms is to at least visualize whether or not, these data point and that data points or those data points are like definitely the outliers, or maybe it could be this one as well. So sometimes I'll put this way: the hat matrix and also the Cook distance are actually much more useful tools for me, because you can use these to identify those outliers. But still, after you know that they could be or they may not be, to know that, you still have to manually check it. But at least you can definitely cut off some term. And if some of these points are somewhat important, you can put the weight down. You can use weighted least square to to put down to reduce the effect of those outliers. That could be one way as well. Like, you don't need to apply the algorithm like totally exactly as it is. You could use combined of the method to handle the situation. And finally, we have provided summarize for all the techniques that we've learned today, and also for a little thing. You may notice that, I mentioned like the method that I just said, that the least trim square is like other robust regression method that you may consider. In fact, there are other algorithms like random sample consensus or RANSAC. These are actually still being used in many applications, and usually they are used to cut off those outliers based on the overall population. Least median square is another one, and I kind of remember roughly is similar to LAD. Least absolute deviation. Maybe just have a look at them a little bit, but these will not be in your exam. Just know that more than whatever we just learned, there are others. But of course, we should know that the outlier analysis are talking about the algorithm for checking outliers and try to find where they are and remove them. But the robust estimation, which I misspelled this one, are more about proposing loss function that put less emphasis on the outliers. Meanwhile, the iteratively weighted least square are the one that adjust the weights towards minimizing those residual. Okay, and probably that's it. And we have homework for you. I think it's homework number 2, to try and check if you understand how to compute the hat matrix and the Cook distance. And probably this could be something that got into your to your midterm exam. So just have a look at it, and yes, don't forget to do your homework. Bye.